Hello, this is Ashley Gibbon. I'm the development manager, and we're here today to talk about the principles of accuracy. This is the third in a series of trainings that we're doing on the different parts of validation. So the topics for today are sources of laboratory error, how do we measure accuracy, how do we know it's correct, testing accuracy during validation, monitoring accuracy once the assay is in production, and then using accuracy in troubleshooting. I would argue that out of all the parts of validation, that accuracy is the most important. So if you think about all the pieces of a validation, you could have a perfectly linear assay with great sensitivity, great precision, good characterized reference population, long sample stability. But if you're not getting the right answer, then the rest of that really doesn't matter. So we talk about accuracy early on in validation. It's one of the first things we talk about. We talk about it regularly throughout validation, and then we talk about it and check back in on it regularly once it's in production. And the CLSI, the Clinical Standard Laboratory Standards Institute, tends to agree with that. There are actually 12 different documents that refer to different types of accuracy in the laboratory. So first I wanted to recap quickly the difference between precision and accuracy. So precision we talked about last time, and if you remember, this means if we take the same sample and we run it multiple times, do we get the same answer? Accuracy is a measure of correctness. If I take a sample of known value, do I get the correct value? And we use this slide to illustrate the difference. So what we hope to get, obviously, is high accuracy, high precision, like the bottom right-hand bullseye. Sometimes what we get is the top left-hand side, the low accuracy, low precision. But understanding if you have an accuracy problem or a precision problem is very helpful when you're starting to troubleshoot a problem. So our last training where we talked about precision, we were talking about situations like the bottom left-hand bullseye, the high accuracy, low precision, where we were getting basically the right answer. We were just getting different answers every time. Today we're going to talk about problems with accuracy, so the top right hand bullseye. Like imprecision, inaccuracy can come from many places in the lab. However, unlike precision, it's a lot more difficult to narrow down the individual contributions to laboratory error. So if you remember when we talked about precision, in the validation, we like to isolate individual sources. So we want to look, for example, just at imprecision from the sample prep and hold everything else constant. Or we might be looking at just the imprecision coming from the instrument and holding everything else constant so that we can isolate the individual contributors to understand the larger whole. The problem with trying to do this with error is that it just comes from so many different places, and so much of it is just human error. So here's some examples of error that I've seen at Genova, and this is by far not a comprehensive list. This is just to illustrate the different types of errors that we see sometimes. This could be things like dilution errors or calculation errors. This could be a sample that gets misaliquoted into the incorrect tube. This could be someone walks by your benchtop and accidentally knocks off your pipette, it hits the floor and some internal mechanism breaks and you don't realize it and you pick it up and you keep using it. It's these sort of random human error. And the problem is that during validation, we're never going to be able to isolate these sorts of errors and then measure them and account for them. So these sorts of errors are called random error. They're unknown, they're unpredictable, they're usually one time, meaning if you were to start the process over from the very beginning, you probably get a different answer at the end. These are the mispipetting wells. Say you're loading your vials onto the instrument and you accidentally swap two vials, that sort of thing. And so when we can, we want to try to reduce the likelihood of a random error. So like I said, there was not much we can do to measure it, but I think it's helpful to have it always in the forefront of your mind when you're validating a test. So once it's in production, the supervisors are going to be thinking a lot about how to reduce human error. But we as development techs, in validation, it's important for us to be thinking about our assay and saying, where are the most likely steps that an error may occur? Where is there a place where I'm adding multiple reagents together? Is there a step where I'm having to adjust my pipette and maybe I'll forget? If it's a long procedure, say a 6 or 7 hour sample prep, where are the most likely places that somebody's going to stop for lunch or for a coffee break? And then how are they going to know where they were when they came back? That sort of thing. But for the most part, there's not much we can do about measuring this during validation. The other type is systematic error. And these are errors that are inherent within the assay. And these are things that we can measure and try to control during validation. So these are errors that if we were to repeat them, they're going to get the same answer. So this is something like an incorrect calibration. Say we get a new lot of calibrators and the target value is 25, but in actuality it's about 28. And so everything's going to move up slightly. It's those sorts of things, interference, drift. These all come together in what CLSI calls total analytical error. And they have this cool grid that sort of shows the tree. So if you look at the diagnostic accuracy, there are pre-analytical and post-analytical errors that can occur. There's not much we can do about that. Pre-analytical will be things like, the patient collects their sample incorrectly. We cannot account for that in what we do. Post-analytical errors are usually things like transcription errors or data entry errors, those sorts of things, which is why in the lab we use a laboratory information system, SCC, to reduce as much as possible those sorts of errors. So if you think, a lot of our instruments take the data straight from the instrument, transfer it straight into SCC, and then SCC creates the report from that. So it minimizes human input. Then if you move down the tree to total analytical error, they break it up into the random and the systematic. The precision we talked about last time, the precision sources, there's also random interferences. These are things like you're in the middle of your prep and you get an emergency call on your cell phone and you have to step away. When you come back, you can't remember where you were and you accidentally pipette that reagent twice. Those sorts of things that, again, we can't account for. On the systematic error side, this chart breaks it down into protocol specific and protocol independent. These on the specific side, the drift, the sample carryover, and the reagent, we're going to talk about those in a future training on interferences. And these are the studies that we look at during validation. So again, we'll talk about interferences in a future training. So how do we measure accuracy? We look at error. So it's calculated by subtracting observed minus target divided by target and multiplying times 100 to turn it into a percentage. The nice thing about this calculation is it also tells us the directionality of the error. For example, if our target was 10 and we actually observed 9.63, this tells us that our observed value that we measured on our instrument was actually lower than the target value. So that gives us a negative 3.7% error. And on the flip side, if the error comes out positive, then it tells us that our observation was too high. In this example, our target was 10, our observed was 13.42. So you work out the equation, you get a positive 34.1%. So this is helpful understanding the positive negative piece, because when you're looking at a large data set and you're just optically scanning down a row of error, you can sort of take a look and see, do I have mostly negatives? Do I have mostly positives? Or is there a nice balance? And this is going to give you an early clue about whether you have some sort of systematic bias in your assay. So how do we know what's correct from the beginning? Like I said, we talk about this early on, starting with our calibrators. And if you recall from our linearity training, we talked about making sure that you've got your calibrator set that's tied to some sort of reference material. So you always have your calibrators and then you have a second source material. And we like to use for a second source material, if possible, the gold standard is certified reference materials from the NIST, the National Institutes of Standard and Technology. And this is an internationally recognized body that creates stock solutions, and so we know that they're used all over the place, all different platforms by lots of different companies. So we have a high confidence in that value. They come with nice certificates of analysis, so you know exactly how much your target value is. Unfortunately, a lot of what we do at Genova is more esoteric, and so these sorts of um, gold standard materials don't exist. So when they don't, then we need to look for alternatives. So when possible, we use materials with internal certification programs. So there are manufacturers who make calibration kits and they have their own internal certification, which while not a NIST standard, it's still, a second laboratory that tested the same material and got the same value as us. They usually give some sort of um, certificate of analysis too. We have used proficiency testing to samples to check that we're in the right ballpark, but at a very minimum, we have to use a second source material to confirm. So if our calibrators are from Sigma, then we need to get something from some other company, Fluka or Cayman Chemicals or something else. And so this tells us if there's two different manufacturers of the same chemical and we run them against each other as unknowns and we get the same value, then we have pretty good confidence that we've got the right value. So how do we test accuracy during validation? We have a checklist for FDA and non-FDA approved, and there's 3 steps under accuracy: interference, method comparison, and recovery. Like I said, we'll cover interference in a future training. This is a really big topic with lots of tentacles. So today we're just going to talk about method comparison and recovery. So starting with method comparison, we use a minimum of 40 samples, and this is exactly what it sounds like. We have 2 different methods and we do split samples. So we want samples that span the reportable range of the assay, which we determined in our linearity. We want to make sure that some of the samples are outside the expected reference range. If we have an idea of what normal is going to be, let's get some normal samples and some abnormal samples, as long as it's all within the reportable range. We want to take those samples, split them, and then run them on both methods. Now, the most important thing with method comparison is to make sure that we keep as much constant as possible. So whenever possible, run the two methods at the same time by the same tech within the same sample stability, meaning if you have one sample that's got one freeze thaw, the other sample better have one freeze thaw. You don't want to mix those two. So you don't want to thaw your sample, run method 1 on Monday, and then leave that sample in the refrigerator and run method 2 on Tuesday, because suddenly you've just introduced an additional variable. You want to keep the only variable being the 2 different methods. Does that make sense? So we know this isn't always possible, because sometimes you've only got one person, but as much as possible, keep things constant. So when we talk about method comparisons, comparison method can be a different methodology. This could be like an RIA versus an LCMS. It could be a different kit manufacturer, say an ALPCO EIA versus an IBL EIA. It could be a different laboratory. We could split it with one of our competitors. So this tends to be kind of expensive. Oftentimes when we're validating, say, a manufacturer's kit, the manufacturer, if we reach out to them, they will get us in touch with another laboratory to do splits with, or they will do splits with us in their laboratory. So it's at least worth reaching out and asking. The important thing when you're selecting the comparison method is just to make sure that it's tied to a traceable standard reference material. So you don't want to send this to some unknown lab that we don't know anything about. You want to make sure that we have confidence in the results that we're getting back from this comparative method. So once you run your samples on both method, we want to take a look at the data by plotting them on a comparison plot. You always put your reference method on your x-axis. You always put your knowns on the x. And then put our testing method on the y. And this is pretty standard across data analysis. You always put your known on the x and your unknown on the y. And then we're going to look at a regression. So it might look something like this. This is the comparison we did, the Aeroset versus the Architect, which were 2 different types of instruments. So you can see it actually has a pretty tight correlation. So we're looking at slope, intercept, and R squared. And you can remove obvious outliers. You can see there's one point down below the line that we probably could call that an outlier and drop it out. So the other thing to think about when method comparisons is that ideally you want a slope near 1, intercept near 0, and an R squared as close to 1 as possible. But method comparisons, you may not have a perfect slope. Really what we're interested in method comparisons are how are the two methods related to each other. So in this case, we're looking at LCMS versus RIA, and you can see the slope is 0.43, which is showing a low bias on the LCMS method compared to the RIA. But this is not necessarily bad. It's just showing us the relationship between those two methods. And in this particular case, we knew from doing literature searches that the RIA that we were using had some inherent interference, some non-specific binding that was causing the values to be artificially a little bit higher. And so there have been lots of other articles in the literature for people who had switched from RIA to LCMS and were finding that they were getting values of about half on the LCMS that they were on the RIA. So we knew that going into this. So we did the method comparison, we got a slope of 0.43. That's pretty close to half. So that's not necessarily bad is my point here. Really, when you're looking at method comparison, you want to see how closely are those points clustered around that line, which is what's represented by your R squared. It's also helpful to create a difference plot. So for example, if this was your data, we have cysteine on our comparative method or a testing method. We calculated the difference between the two and then the percent error. You can sort of scan down. You see there's some negatives and there's some positives, probably a lot more positives than others. And if we put that in just a, you can see we get a pretty nice R squared of 0.98. The slope, though, is about 1.13, which is suggesting that we have a positive bias. So in order to better characterize what this data is telling us, we plotted in a difference plot, which looks like this. So the x-axis is the concentration of the known method, the comparative method, and then on the y-axis we plot the error, the percent error. And so the way to read this is to look, as you read across the concentration, what is the percent error doing? So you can see in this method, at the very bottom end, at the very low concentrations, we're getting negative percent errors, and actually pretty high negative percent errors. But somewhere around a concentration of, I don't know, 3 or 4, maybe 5, it flips. And from about 5 and greater, the concentrations typically are having errors that are on the positive side, somewhere around that positive 10 maybe. So this is sort of just showing what this assay is doing. And in this sort of situation, I might go back to my linearity and say, let's look at the bottom end. Maybe our sensitivity really can't go down that low. Maybe the bottom end of this assay is really somewhere around that 3 point. Here's what you're hoping to see is a pretty equal distribution of your percent errors across the concentration range. So this data is telling me that no matter what concentration of cysteine I'm looking at, I'm going to have a percent error somewhere between, negative 16 and positive 18. So within 20% on either side. So it's pretty well balanced. It's concentration independent. Here's an example when you might have a percent error that shows a trending. So this is showing that at the bottom end of the assay, we're having negative percent errors. It flips somewhere around 10 and then just continues to grow. But if you look at the actual percent errors, all of these points are within 20% error. So this is where a difference plot is helpful, because if you were just looking at the data points, it'd be very easy to just scan down the data on those 40 patient splits and say, you know what, all of our percent errors are within 20%, we're good to go. But without plotting it like this, you would never catch that it's concentration dependent, your accuracy. You can also get something like this, where you can see the percent error is within 20% up until about a concentration of 30, where it just sort of falls apart in both directions. So in this situation, again, I would go back to my linearity and say, this is indicating that we might not actually have linearity above about 30. And sometimes it can just look really crazy like this. And if you ever see something like this, come find me, because this is, I'm not sure what this is. Now, having a known bias on your assay isn't necessarily bad. It's important to understand what your bias is, but as long as you can characterize your reference range around that, it's not necessarily a bad thing. So let's say you had something like this, a cysteine, which regardless of your concentration, has percent error around that 5% mark. So if we were to launch this assay, we just know that against other certified reference materials, against other standard methods, we have an inherent bias of about 5%. When you see something like this and it's very well balanced, the CLSI guidelines recommends looking at this at a frequency plot as well, which looks something like this, where I took that same data in a frequency plot, and you can see it shows a really nice Gaussian distribution with the highest point right at that 5% error. It's the same data, it's telling you the same thing. It's just showing that this is a very well-balanced population with a known bias around 5%. So why does accuracy matter? Clinically, we might want to look at accuracy as far as clinical interpretation. For assays where the clinical impact of our results could make a big difference in how the client is treating his patients, we might take a look at something like an error grid. We don't do this for many assays, but we do these for things that have critical results. So you can see we have our comparative measurement procedure, our known on the X, and our measurement on the Y, the assay that we're testing. And this is assuming Y equals X, so we have a slope perfect correlation between the two. And so we've drawn the zone A in green here, and this is indicating where small errors are unlikely to have much of a clinical impact, meaning that if we're off by a couple percentage points here and there, it's going to lead to the same treatment decision. Zone B here in yellow, this is going a little bit further out from the line. So this is saying these are errors of moderate magnitude that could result in altered clinical response. So this could cause harm to the patient. And then zone C, of course, are errors so large that could lead to erroneous treatment decisions that could cause significant patient harm. So, depending on the assay, these zones might be larger or smaller. It may be asymmetrical. Maybe it's only bad if it's the errors high or the errors low. So this is just a generic error grid that we have here. This may be important for assays like potassium, where you're talking about cellular membranes. And so a 20% error in potassium could mean you are dead. Or something like CalPro, where a 20% error could mean the difference between an IBS and an IBD diagnosis, which have different clinical pathways. So we don't look at this in a lot of assays, but we do when there is a significant clinical impact. Next, we look at recovery studies. So recovery studies assess our ability to spike in something of a known value and then be able to accurately measure it again. So we're going to take at least 5 samples. We're going to use our second source material to spike, either what we use for our calibration verification or an aqueous control, something like that. It just can't be the same material as your calibrator. It's good at practice to do several levels of spike. We're going to run each level in duplicate, and we're always going to measure our spike. While you can calculate it mathematically what it should be, it's always good practice to measure it. So I'll show you what that looks like. So say we take 5 blood samples and a blank. We want to try to matrix match our blank if possible, meaning using Serosub or Urosub, something, or a charcoal stripped urine, something that's as closely matched to the sample as possible. If you need to use water or diluent, that's fine too. But if you can introduce more of that matrix material, then that's going to better match what's happening in your samples. And then for each one of those samples and blanks, we're going to make 3 aliquots. In this example, I did 1 milliliter of aliquot in each. And then of the 3 aliquots, 1 we leave alone, 1 we spike at a low level, 1 we spike at a high level. In this example, I used a 50 microliter spike and a 100 microliter spike. And this is going to give us 18 tubes. For each of our 5 samples in our blank, we'll have a base, a spike 1, and a spike 2. And we're going to run each of these 18 samples in duplicate. So the data analysis on this. So we have our samples 1 through 5 in our blank. We ran the base, the one that didn't get any spike, in duplicate, so you can see our observed values here, and then we calculated the average of those observed values. We then took the spike 1 level for each sample and ran it in duplicate. You can see the observed values here and then the averages. So then how do we calculate what the target value should have been? Well, let's think about it. What was in that first sample 1, spike 1 vial? You have your base value, you have your base sample, plus you have that little bit of spike. Now when you added that 50 microliters of spike into your 1 ml of blood, you did introduce some level of dilution, so we need to account for that. So our target is the average base times the dilution of the base plus the average spike. So we have base diluted plus the spike. In the sample 1 example, it's 47.97. Our dilution is 1 milliliter of the base out of a total volume of 1.05 milliliters, because 50 microliters. That accounts for our dilution, plus the 11.42 that came from our blank. We don't have to account for the dilution in our blank because we spiked that water or that Serosub in the same way that we spiked the patient. So we've already accounted for the dilution of the spike material. And so that gave us a target value of 57.1, and we actually observed an average value of 59.59, which is a recovery of 104%. So recovery is observed divided by target and times 100 to make it a percentage. So you can see in this situation, we had something funny going on with sample 4, the second observation. It's 62.43, which is more than twice what we were expecting. So in this case, I would probably say that's most likely an outlier. And so then if we drop it out, our recovery goes to 104. So another point here, just good lab practice, is if you are going to identify an outlier, it's good to keep the number in there. So in this case, in the cell, I typed the text OL for outlier. And if you add text to a cell in Excel, it drops it out of the calculation. So it ignores it as far as the recovery and average calculations. But it still allows us to see what the original value was. So that way, when you go to submit your validation to your lab director, they can look and see if that was an appropriate outlier to drop or not. And then here's the same calculations using spike 2. Though remember, spike 2 at 100 microliters instead of 50 microliters, so you need to adjust for that dilution. So there's two important considerations when you're doing recovery studies. One is that the volume of your spike should not exceed 10% of your base volume. So for example, if you have 1 milliliter of blood, you should never do 100 milliliters of spike, because then you've just diluted your blood sample 50%, and this is going to dilute out any potential matrix effect. And you want to make sure you're maintaining that in your recovery study, because matrix effects can affect the accuracy of your method, so you don't want to dilute that out and then not be able to see it. Also, you want to make sure that you don't overwhelm or underwhelm your sample with the concentration of your spike. So you need to consider whether those measurements are within the imprecision of the assay. So, for example, here we had a spike of 0.45, but our base values were 20 to 50. So the observed spike values are pretty much the same as the base values by themselves, or within the imprecision of the assay. So you can see we had a target value of 46.13 and an average value of 47.72. So they're basically the same number. We can't really tell the difference between those two numbers within the imprecision of that assay. On the other hand, we have a spike of 600 when the base is 20 to 50. And so the observed base plus spike values is pretty much the same as the spike alone. So our target values, you see, are all in the low 600s, and our spike is in the low 600. So we've completely overwhelmed the concentration in the sample with the amount of spike. So we got great recoveries, but this is kind of cheating, and this isn't really looking at what it's going to be like in your assay. So for this reason, recovery studies are very difficult to set up. It takes a lot of planning ahead of time. You have to have a good idea of where your patients are going to fall so that you can calculate appropriate levels of spike. You need to make sure that you do the math correctly so that you're spiking in the correct amounts. You know what your targets are going to be. This is the most common experiment that we have to repeat in validation because we just didn't get it quite right. Spike was too high, spike was too low, the samples didn't have anything going on. So for this reason, it's good lab practice to draw up your plan, double check all your calculations, and then have a coworker double check the calculations as well, just to make sure that you've got the numbers where you expect them to be. It does happen sometimes that for whatever reason, the spiking doesn't work. So some examples that I'm aware of is we had an assay that was used red blood cells. And so if you try to spike a water sample into a red blood cell, you're going to lyse all your cells. So that didn't work. There are examples where the analyte levels are so low that we just can't get the spike low enough to not overwhelm the sample. So in those situations, we'll do something called a matrix recovery. And recovery levels can be created by proportionally mixing high and low samples. So in this example, the 100% A is a high sample and the 100% B is a very low sample, and we're going to mix them in these various proportions. So your calculations are going to look something like this: your percent A and your percent B, your observed values in duplicate, and then your average values. And so then to calculate your target value, for example, the second line down, target value of 41.02 is just 80% of that 47.97 and 20% of that 13.215. If you're going to do a matrix recovery, it's always good practice to do this several times as well, just so you're sure that you didn't just get lucky with two good samples. You also want to make sure that the two samples are distinctly different values. I've certainly done that before, where sample A was 29, sample B was 27, and all the levels were 28. And while the recovery looked great, the lab director sent it back and had me do it again. So once an assay is live in production, there are multiple ways that we monitor accuracy. So every single batch has controls, and controls have target values that you have to be within before we can release patient results. So that is a accuracy check at every single batch. Then weekly, the supervisors are doing QC review, and they're looking at how do those controls fall relative to the expected mean. So in this example, that green line, you can see these control points are all falling below that green line. And they're looking for things like trending or shifts. And so if you bring something like that and you see that the patients are running or the controls are running in between those two yellow lines, and then suddenly at that black line something shifted up, then the supervisor is going to question what happened at that time point that might have made everything move. And then we're checking accuracy at every calibrator lot change. We are looking at our old calibrator versus our new calibrator and making sure they get the same value. So again, we're tying that calibrator back to the previous one. Then 4 times a year, there's an intentional accuracy check. Every 6 months, we do a calibration verification or linearity. That is taking our second source material and confirming the values of our calibrators. And every 6 months, we do proficiency testing on every assay. And this is where we take a known samples, usually 3 to 5 samples of known value, and run them as unknowns through the lab to make sure that following through the whole process, we're getting the values that we expect. Now, the Office of Quality maintains lots of information on proficiency testing and external proficiency versus internal proficiency. So I'm not going to go into it more than that today, just to say it gets checked at those periods. And then we do periodic patient review, and this is it varies by department and by supervisor and by site. But this is at some frequency where we check the patients and see how they're trending. And so all of these things keep the assay tied back to the validation and reference range. So if you think about it, we do this huge validation with all these accuracy and precision and linearity studies, and then we run this huge reference range to make sure we understand what normal is. It's a tremendous amount of work to do a validation. And so by checking the accuracy throughout production at each of these different steps, it means that we don't have to continuously confirm validation. We're not having to continuously do recovery studies and method comparisons and redo reference ranges, because we've got all these anchors that tie us back to the validation. So we know that the assay is where it was when we reference ranged it. So this is why if things shift and we've moved off of the reference range, then we've disconnected ourselves from the validation, and that's bad news. So for that reason, never change calibrator lots and control lots at the same time. If you've got multiple controls, it's good practice to only change one control lot at a time. So that way you've always got at least one tie back. You're not changing everything all at once. Because if you change all your calibrators and all your controls at the exact same time, then suddenly you've lost that tie and something could shift and you might not see it. The exceptions to this are some of our manufactured FDA kits. Sometimes the kit manufacturer will change lots of calibrators and controls at the same time, but that's why we maintain very rigorous lot-to-lot testing to confirm that all the new calibrators and controls are exactly where the old ones were. And this is also why we maintain a second source material as a reference check, so that if something shifts, we have that third party, that second source to go back to and know how to get the assay back to where it was. When we're looking at troubleshooting, we're most likely to identify an accuracy issue during one of these events in production. For example, in controls, the shift, like we see here with the black line, these most commonly come from calibrator changes or reference range or reagent changes, those sorts of things. So if you bring something like this to your supervisor or your manager or to me, we're going to say, if your control shifted like this, did your patients also shift? Because if your patient shifted, then we're looking at something assay-wide, maybe a reagent change, an instrument shift, maybe you did a preventative maintenance on your instrument or you changed the column, maybe there's a new technician on the assay, something like that. If the control shifted like this but the patients did not, then this could be some sort of stability issue or inappropriate controls where your controls are not set where your patients are. But the key point is that something changed. So if you bring this to your supervisor, they're going to ask you what changed. Calibrator lot to lots. So for example, let's say we bring in on a new calibrator lot on our assay. The target values are 100, 50, 25, 12.5, and 6.25. We run them, we get these observed values. You can see the errors are all, somewhere around that -12 error range. So we're seeing a negative bias on our new calibrators compared to our old. So the question is, which one's right? Is it our old calibrators or is our new calibrators? So this is where that second source material comes in handy. So we're not sure which one's right. Let's run the second source material. So here's our second source material against our current calibrator. So you can see we're still seeing that negative 10, 11, 12% error. So that's consistent with what we saw above. So if we take that second source material and run it against the new calibrator set, you can see those percent errors are right on the money. So this is telling us that something happened with our old calibration set and we need to investigate further. If it was the other way around, where it was the new calibrator material that was off by negative 11%, then we might have the options of adjusting the concentration to bump it back up where it should be. We sometimes see accuracy issues when we're evaluating the patient trending. So this is sort of what you're hoping to see. In NICE, this is one of our essential metabolic fatty acids where you're sort of expecting to see patients basically running about the same. And so if you see something like this, where you see it shifted just after the 4,000 mark, that tells you that something happened at that time point that moved all the patients up. So again, we're going to look at things like calibrators or reagents. Again, what changed? Something happened here. Now, it's an interesting story. This particular analyte is part of our EMFA assay, our essential metabolic fatty acids. So these are a lot of your good fats. And it's typically a pretty well-behaved assay. And so one time when I was supervisor over this area, the tech brought me a batch and he said, this batch just looks really funny. And it looks something like this for a number of the analytes. All the patients in that batch had shifted. We're like, well, that's strange. It doesn't usually do that. We went back to the instrument and we checked the calibration curves and they were pretty and the peaks were pretty. But the key point was that the controls were right where they were supposed to be. They were right on target. And so we said, well, that's strange, that the patients would have shifted, but the controls had not. But we couldn't figure out a reason for it. So I said, I don't know what this is. Let's just repeat the batch. And he did, and it came out exactly the same. And we looked at the batch before and the batch after, and they were right where they usually are. And so it was just this one batch. And we investigated a little further, and we realized that this was a research study from Norway, and this doctor was supplementing his patients with omega 3s and omega 6s, all these healthy fats. And so, in some cases, it might just be the samples, but until you're able to rule that out, you have to investigate further. And you could just get something like this. And honestly, I don't know what I would do if I saw something like this, where the assay just sort of fell apart somewhere around that 4,000 mark. This is definitely a call to the lab director. So that's our training on accuracy. You can get training credit in UltiPro by looking for principles of accuracy.